All right, we're talking about polynomial functions and their graphs. And we have talked about polynomials before. We've added, subtracted, multiplied, divided, factored polynomials. What do you remember what had to be true about the exponents of a polynomial? What made it a polynomial? No. Plain old x by itself is a polynomial. What could you not have as an exponent in a polynomial? Couldn't have negative exponents, and you also couldn't have fractional exponents, right? So polynomials were sum or difference of terms of the form some number times x to a power, where the power had to be a non-negative integer. So that's what goes in the first blank. The exponents must be non-negative integers. Integers mean whole number, either positive or negative. Why didn't it just say positive integers? What's the difference between non-negative and positive? Zero. You could have zero as an exponent. So the exponents have to be non-negative integers. The highest exponent is called the what? The degree of the polynomial. And the coefficient of the term with the highest power is called the it's two words, and the second word is coefficient. The coefficient of the term with the highest degree is called the not necessarily, because it's not just whether it's a 7 or a 2, but it's the leading coefficient. No matter in what order the terms are written, it's the coefficient of the term with the highest power is called the leading coefficient. The term with the highest power is called the leading term, even if it's in the middle, even if it's in the end. The term with the highest degree is called the leading term, and its coefficient is called the leading coefficient. So you have some examples in the book of things that are polynomial functions and things that are not polynomial functions. In the second column, -3 square root of x couldn't be part of a polynomial function because that's a fractional exponent. And here, when you have an x in the denominator, that's not a polynomial because that indicates a negative exponent. Square root of 2 is not a problem because I don't have to have integer coefficients. I just have to have integer exponents. All right, another thing to know about polynomials is they have nice, smooth, continuous graphs. Now, we'll talk about continuity in calculus, but it turns out that, that most important thing in calculus, the derivative, you can take the derivative of nice, smooth graphs, all the graphs of polynomial functions, or all polynomial functions, you can find the derivative, but you cannot take the derivative of functions that have discontinuities like this or sharp turning points like that. So because polynomials are all not have nice, smooth, continuous graph, you can find the derivative of any polynomial function. That's the second thing in the notes. Polynomial functions are smooth and continuous. They don't have any skips or jumps or sharp turning points. All right. Here are 4 polynomial functions that we've already graphed. I used y instead of f of x, that doesn't matter. But these 4 were in our library of functions. So go ahead and graph these 4 polynomial functions for me in those 4 spots. Just really quickly. Is that what you have? X cubed was that vertical uphill snake. Negative x cubed was the same graph, but flipped with respect to the x-axis. So you can call it the downhill snake. X squared is a concave up parabola. Negative x squared is the concave down parabola. Well, it turns out that no matter how big and ugly of a polynomial you have, it has to be doing one of these four things on the end. That's really all anything could do on the end. You know, if I ask you, how many different directions can you point your hands, your arms? Well, you could have them both up, you could have them both down, you could have left down, right up, or you could have left up, right down. That's the only thing you can do with the ends of your extremities, and that's the only four things that can happen with the with polynomial functions on the end. And it turns out that which of those four things is going on is determined by whether the degree of the polynomial is even or odd, and whether the leading coefficient is positive or negative. So if you want to know what's going on with the function, at least on its ends, not in the middle, but on the ends, you look at the degree and the leading coefficient. It turns out that if you have an odd degree polynomial with a positive coefficient, at least on the ends, it's going to look like x cubed. It's going to be falling on the left and rising on the right. It doesn't matter whether that's x to the 9th or x to the 11th or x to the 99th. It's still doing this on the ends. If you have an odd degree with a negative coefficient, at least on the ends, it looks like negative x cubed. It's going to go up on the left and fall on the right. If you have an even degree polynomial with a positive coefficient, it's going to, on the ends, look like x squared, both ends going up. And if you have a positive, or excuse me, an even degree with a negative exponent, then both ends are going to be going down like negative x squared. One thing that might help you is to remember that even degree polynomials do the same thing on both ends. Either they both go up or they both go down. Odd degree polynomials do the opposite thing on their ends. All right, let's look at these examples on page 342. I'm going to show you these objectives one at a time like they're laid out in the book, but we're not really going to work some problems until we get to those problems that put everything all together. So in example 1, we have an odd degree polynomial with a positive coefficient. And sure enough, its graph goes down on the left and up on the right, just like x cubed. So what about this checkpoint 1? How would what would the end behavior of this graph look like? Which one of our big four would it look like? It's even degree, so it does the same thing on both ends, and the leading coefficient's positive, so it goes up on both ends like x squared. And example 2, make sure when you're getting the degree of this polynomial, you count the degree of all the x's as if they were all multiplied together. This is actually an x squared if you multiply x minus 1 times x minus 1. So this is 3rd degree. 2 more x's would make it 5th degree. 1 more x would make it 6th degree. This is a 6th degree polynomial with a negative coefficient. So which one of our big 4 does it look like? Both ends going down like x squared. And I thought they would, well, they may have graphed it on the next page, but then again, maybe not. Maybe they're just showing you both ends go down. All right, so I think you have that. Back to the notes. Now that we know how to determine the end behavior of a polynomial, let's talk about the other things we usually find when we're graphing. Usually we find a y-intercept by doing what? Letting x be 0, and we find x-intercepts by doing what? Let y be 0. All right. I think we've used this term before. The zeros of the polynomial are whatever makes the function equal to 0. Just set the function equal to 0. You'll be finding the zeros of the polynomials, and the real zeros of the polynomials turn out to be what? You set the whole thing equal to 0, what are you finding? You're finding the x-intercepts. This is the same as setting y equal to 0, because y and f of x are interchangeable. So the real zeros of a function are its x-intercepts. And if the function has any imaginary zeros, they're not on the graph in a two-dimensional plane. So we're only going to be graphing the real zeros of a function. All right, a little bit more terminology. If x minus c to the nth is a factor of the function, if you factor a function and get x minus some constant to the nth power, then n is called the multiplicity of that 0. Multiplicity refers to the exponent of the factor. And that multiplicity, whether it's even or odd, tells you something important. If the multiplicity is even, then the graph touches the x-axis but doesn't cross it. It looks like this. It's either coming down, hits the x-axis, does a U-turn and goes back up, or it could be coming up, hit the x-axis, does a U-turn and come back down. But the graph touches at that point, doesn't cross. And if the multiplicity is odd, then the graph crosses the x-axis at that 0. It could either be coming up from the left, cross the x-axis, keep going, or it could be coming down from the left, cross the x-axis, and keep going. All right, we'll talk more about that when we get to these problems on the back. Let me go ahead and mention objective 6. It's important. We're not really going to use it. It's important in solving other theorems in calculus, and it can tell you how to find the zeros of a polynomial, but it's not the most efficient way to find the zeros of a polynomial. It just says if f of a and f of b have opposite signs. All right, that's two different y values. The y value when x is a and the y value when x is b. If those two y values have opposite signs, let's say f of a is up here and f of b is down here. Now, based on the fact that polynomials are continuous, they don't hop, skip, or jump, to get from here to here, you have to cross the x-axis somewhere. And so what the intermediate value theorem tells us, I gotta sneeze, excuse me, is if f of a and f of b have different signs, then there has to be at least one real zero somewhere between a and b. It doesn't really help us find that 0. It just tells us there has to be one. All right, last thing before we get to our examples. Understand the relationship between the degree of a polynomial and the number of turning points on the graph. I bet one of my Cumberland County folks remembers, and maybe your college algebra teacher stressed this, but an nth degree polynomial, do you remember how many turning points it can have? One less than the degree. So an nth degree polynomial has at most n minus 1 turning points. If you give me a 4th degree polynomial and then you graph it, and it kind of looks like Loch Ness Monster, that's too many turning points. This is a turning point. It was going down, starts back up. This is a turning point. That's a turning point. That's a turning point. That's a turning point. A fourth degree polynomial cannot have that many turning points. So that wouldn't be correct. Just something you can check your answer with. All right. I have edited the problems in the homework a little bit. If you looked in the book, these problems also said, is the graph symmetric with respect to the x-axis, the y-axis, the origin? We didn't really talk about symmetry. So these are the things that I'm going to be looking for in the homework, and that's what I'll be looking for on the test. We're going to get the end behavior of the graph by looking at the leading term, whether the exponent is even or odd, whether the coefficient's positive or negative. We're going to look at the maximum number of turning points is always going to be one less than the degree of the polynomial. Then we're going to find the y-intercepts by letting x be 0. We're going to find the x-intercepts by letting y be 0. And we will also look at the multiplicity of each of those zeros to say whether the graph touches or crosses at those zeros. And then we'll put it all together. What we're going to end up being able to do is get a pretty darn accurate and quick graph of polynomial functions that we have not graphed before. All right, so I've got 3 good examples. First one, negative x to the 4th plus 4x squared. What's the degree of that polynomial? The highest degree, highest exponent is 4. So it's a 4th degree polynomial with positive or negative leading coefficient? Negative leading coefficient. Now don't be thrown off when we get to this second problem. 6x is not the leading term. The leading term is not the term that's written first. It's the term with the highest degree. So just keep an eye out for that. But here, leading term does happen to be written first. So what's the max number of turning points for a 4th degree polynomial? Yeah, if it has more than 3 squiggles in the middle, I've messed up. Now, I don't know if I'll be able to see it very well on camera, but if you were all here in person, I would say with your arms, and maybe you still can, with your arms, show me the end behavior of this function. Even degree, negative coefficient. What's it going to do on the ends? Everybody in the privacy of your own home, have both ends going down, just like negative x squared. Yeah, it may be easier for us to use fingers here than arms. That's a good idea, Chastity. Its end behavior is just like that of y equals x squared. Now, how do I find the y-intercept? Let x be 0, and usually I can do that without writing anything down. I can see if I let both of these x's be 0, I'm just going to have 0 plus 0 is 0. So that's the y-intercept. Now, when we get down to example 3, it's going to be easy to see the zeros of the polynomial because it's already factored. If it's already factored, I can set each one of these factors equal to 0 in my head. But if this is not already factored, then that's the first thing I need to do so that I can see the zeros. So factor that polynomial. How could you factor it? You can either take out a positive x squared or a negative x squared. It doesn't matter. I usually factor out a negative. Oops. 2 parentheses there. If I factor, hang on to that thought just a minute. I know what you're thinking. I'm factoring out a negative x squared, and that would leave me a positive x squared minus 4. Double check that. Negative x to the 4th plus 4x squared. And then that will factor further into negative x squared times x plus 2 times x minus 2. Actually, Miss Chastity, I can think of 2 things you might have been thinking. Did you realize that left us the difference of 2 squares and we're going to be able to factor further? Okay, I thought you were going to be confused because the sign of the leading coefficient's no longer negative, but it is. If you multiply that out, your highest degree term still has a negative coefficient. All right, when you have a polynomial in factored form, you should be able to look at it and say, if I set each factor equal to 0, what am I going to get for the 3 zeros of this polynomial? Zero, -2, +2. Doesn't matter in what order you write them. I like to put them in order smallest to largest because that's how I'm going to graph them. I graph left to right. Now remember that word multiplicity on the front page. The multiplicity of a graph refers to the exponent of each factor. And if the multiplicity is even, the graph touches the x-axis and does a U-E. If the multiplicity is odd, the graph actually crosses the x-axis. So what's the multiplicity of the 0, -2? Which factor gave us that 0? No. It's when we set x plus 2 equal to 0 that we got that -2. So what's the multiplicity of that 0? The exponent of that factor is 1. So the multiplicity is 1. And the fact that that 1 is odd tells you the graph does what at -2? Odd multiplicity means the graph crosses the x-axis. Now, which one of our factors gave us 0 as a 0 of the polynomial? The x squared did. It's when we set x squared equal to 0 that we got 0. So what's the multiplicity of that 0? The exponent of that factor is 2. And when you have even multiplicity, what does the graph do with that 0? Touches. All right. Which factor gave us 2 as a 0? It's when I set x minus 2 equal to 0 that I got the +2. So what's the multiplicity of that 0? 1. And the graph crosses at 1. Now, it took us a few minutes to write all this down because I asked you to write it down. I asked you to show your work. But if I had not had asked you to show all your work here, really all you had to do was factor the polynomial so that you could see its zeros. And go ahead and plot those zeros, -2, 0, and 2. The y-intercept was 0, 0. I already have that plotted. You could have told without writing anything down that this polynomial was going to go down on both ends. So go ahead and attach the end behavior of that function. Plot the intercepts first, then attach the end behavior, and then do whatever you're supposed to do at each x-intercept. What are you supposed to do at -2? Cross. How far up should I go? Well, it doesn't matter in this class because we can't know that without calculus. That's one of the things calculus is for, is to find those high points and low points. So all I can do here is say it goes up and then at some point it comes down. I really don't know how high it goes up. All right, what's it supposed to do at 0? Touch, and that means touches and does a UE. And once again, I don't know how far up it goes. It may be the same height as that. It may go up higher before it comes back down. I'm just gonna say it goes up that high. Actually, on this one, I can tell that that those 2 points will be the same, those 2 high points. I don't know what they will be, but because both of these exponents are even, when I plug in a positive 1, I'm going to get the same as if I plugged in a negative 1. When I plug in a positive 2, I'm going to get the same thing as when I plug in a negative 2. So I was thinking ahead a little bit and happen to know those are symmetric, but if on your graph they don't look the same height here and here, that's fine. You could have, after you factored, you could have done that whole graph without writing anything else down. All right, any questions on that one? Easy breezy. All right, let's do another one. Number 2, again, it's written in ascending order. So it turns out the leading term is actually at the end. You could turn it around if you wanted to. You're also going to need to factor it to find the zeros. So what could you factor out of that second polynomial? You could either factor out an x and leave it in the form that it's in, or you could factor out a negative x and put it in descending order. Absolutely doesn't matter. I think I'll do the latter. I'll factor out a negative x and say negative x times x to the 4th will give me that x to the 5th. Negative x times positive x squared will give me that negative x cubed. And negative x times negative 6 would give me that positive 6. Just check your factoring. That's negative x to the 5th minus x cubed plus 6x. I'm good. It may factor further though. And I don't have a problem factoring something with higher exponents. As long as I can find factors of 6 that have a difference of 1, I can factor that further. Instead of the first term of each of those factors being just x, what would they have to be in order to give me an x to the 4th? They just both need to be x squared. And then factors of 6 that have a difference of 1 are 3 and 2. And to get a positive 1 in the middle, I need a positive 3 and a negative 2. To fold that back together real quickly and make sure it's still equivalent to what I started with. All right. Will it factor any further? No, this would be difference of 2 squares, except for 2 is not a perfect square. So that's factored as completely as possible. Now, when I'm looking for the end behavior in the y-intercept, I'll probably look at the unfactored form of the polynomial. That's where it's easiest to see its 5th degree with a negative coefficient. And since it's 5th degree with a negative coefficient, what's it going to do on the ends? It's going to look like negative x cubed. It's going to go down on the left. No, I'm sorry, up on the left and down on the right. Just like negative x cubed. Fifth degree, leading coefficient negative, with no more than how many turning points? Oh, this could have 4 turning points. That's actually why I didn't join the pieces here. It may have up to 4 squiggles in the middle. All right, the y-intercept is easiest to find in the form where it's not factored, because you can plug a 0 into each of those place of each of those x's and see real quickly that once again the y-intercept is 0. Now, what are the zeros of this polynomial? What do you get if you set negative x equal to 0? You just get 0. What if you set x squared plus 3 equal to 0? And what does that tell you? You have 2 imaginary zeros. We're only looking for the real zeros because we're graphing. If we were doing something else, we might be able to use those imaginary zeros, but not to graph. So this gives you 0, this gives you imaginary, and what about x squared minus 2 equals 0? Plus or minus square root of 2. So our 3 real zeros are negative square root of 2, 0, and positive square root of 2. You don't have to list them in that order, but that's how I'm going to graph them, so I did. All right, what's the multiplicity of the 0 that gave, or what's the exponent of the factor that gave me negative square root of 2 as a 0? You have to be careful with this, that actually will factor into x plus square root of 2 times x minus square root of 2. Yeah, each one of those has an exponent of 1. So each one of those zeros has a multiplicity of 1. You're looking at the exponent outside the exponent to which that whole factor is raised. Yes, Ms. Chastity. And we're actually going to write it like that in 2.5 tomorrow. Yeah, if you wanted to take this further, you could go negative x times x squared plus 3 times x plus square root of 2 times x minus square root of 2. If that occurred to you, you could. Heck, for that matter, I could write x squared plus 3 as x plus I square root of 3 and x minus I square root of 3. But I really don't think I want to go that far if I'm just looking for the real zeros so I can graph them. What about the multiplicity of 0? That plain old x was just to the first. So the multiplicity of that 0 is 1. What does that mean the graph does at each one of these intercepts? Yep. Yeah, when you graph it, square root of 2 is darn close to 1.4. So I'm going to graph about negative 1.4, 0, and about positive 1.4. Then attach the end behavior. We already figured out that this graph goes up on the left and down on the right, like x cubed. And then just make the graph cross the x-axis at each one of those zeros. I don't know how far to go down without calculus. At some point, I've just got to turn around and come back up. to hit that next x-intercept. And then the graph has to cross again, and at some point, turn around and come back down to hit that last x-intercept. How many turning points does this graph have? One right here and one right here, 2. That's okay, as long as I don't have more than 4, that's fine. I just don't know exactly how low and high those turning points go without calculus. All right. Any questions? See if anybody else is there that I'm not seeing. Hey, Kobe, you were hiding before I spread that out. All right, last one. Now, when the polynomial is already factored for you, that's very nice. It makes it easy to find the x-intercepts. You might have to think just a little bit harder about what the degree is. But if you multiply that all out, and it would take a long time and I don't want to do it, but if you did multiply it all out, what would the highest exponent of the x's be? You'd have an x times an x squared, that would be an x to the third, and then you'd have another x to the third, so that's a 6th degree polynomial. That's from adding that 1, that 2, and that 3. Woo, yikes, psychedelic. Wow, I'm gonna have to close it and open it back up. Nope, yep. No, I'm choosing it. Well, okay, that got it. I got it. Okay. Sorry about that. Okay. Back in business. So this is a 6th degree polynomial with, what's the sign of the leading coefficient? +3, so it's positive. What do we know about the end behavior of a 6th degree polynomial with a positive coefficient? It's going to look like which one of our 4 basic polynomials? It's going to look like x squared. It's going to go up on both ends. Even degree, positive coefficient goes up on both ends like x squared, with no more than how many turning points in the middle? 1 less than the degree would be 5. The thing that's a little bit harder to find when it's in factored form is the y-intercept. Just make sure you're letting x be 0 in each one of those factors. I'd have 3 times, if I let x be 0 in the first factor, what would I get? Right, I'd get, no, I'm letting x be 0, not letting the factor be 0. If I let x be 0, I'd just get 3. Next factor, if I let x be 0, I'd get -2. Next factor, if I let x be 0, I'd get 1. Again, I wasn't setting the factors equal to 0. I was letting x be 0 because I'm looking for the y-intercept. And it turns out the y-intercept here is -18. Oh, snap. Because I like to make a mistake on the last problem of the day. It's just my thing, my signature. See if y'all are still awake at the end of class. Crap. You buy that? Yeah, that if I let x be 0, that 3 is to the first. If I let this x be 0, I'd get -2, but it's still squared. And if I let x be 0 here, 1 cubed is still 1. So that would not be -18. It would be 4 times 9, it'd be +36. Okay. All right. Now I'm ready to set each factor equal to 0. And if I did, what 0 would this first factor give me? If I set 2x plus 3 equal to 0, I'd get -3/2 with multiplicity what? 1, which means the graph crosses the x-axis at -3/2. All right, when I set the next factor equal to 0, I'd get what? 2, which is a 0 of multiplicity what? 2, which means the graph does what at that point on the x-axis? Touches and does a U-ing. And when I set that last factor equal to 0, I get what? -1 is a 0 of multiplicity. That exponent is 3, which means the graph does what? Crosses. So to graph that, I first plot all the intercepts. My y-intercept 36, I'm just going to have to say it's way, way up there somewhere. My x-intercepts are -1.5, +2, and -1. So these two are close together. Then attach the end behavior. You told me both ends go up. I can do that. You told me the graph crosses the x-axis at -1.5. I don't know how far down it goes, but pretty quickly it has to turn around, come back up to hit that 1. And what's supposed to happen at -1? Supposed to cross again. I don't know how far to go up, but it has to be at least how far? Got to hit that y-intercept. It may go higher than that, but it at least has to go up to hit that y-intercept. I'm going to make mine look like it goes up on past that. I don't actually know. But at some point, it has to turn and come back down. What's it supposed to do at 2? And that is exactly what happened. So the touches, crosses, and the end behavior have to match. If I had crossed at 2, then I would have had the wrong end behavior. But because this graph touched at 2 and went back up, I had the exact end behavior I expected. And that's a pretty accurate graph of that equation, except for I don't really know how low this is, and I don't really know how high that is. Otherwise, it's a pretty good graph. And we could have gotten that graph by probably not writing anything at all down. If you could get that y-intercept in your head without having to write it down, you wouldn't have had to write down anything to get that graph. You would have been able to do it really quickly. All right. Do you think I've kept you late long enough to let you go 10 minutes early one time? I probably owe you 10 minutes. Probably owe you a few 10 minutes. But the homework is 2.3. It's in MyLabs. And then I think, no, not tomorrow, but coming up soon, I've got a homework assignment that's on paper because MyLabs has trouble letting you graph complicated things. Yeah. All righty. See y'all tomorrow. And I